Happy Thursday morning. We've had a great 2 days so far of AEE West and a great day to wrap up today. So we want to thank our keynote speakers for Tuesday and Wednesday, Dr. Martin Keller of NREL and Deborah Smith of Seattle City Light. We've had great virtual expo with our exhibitors, networking. We've had informative conference sessions. I'd like to thank personally all of the attendees, the speakers, the exhibitors for attending and participating in the event. And finally, a huge thank you to the AEE staff who pull off miracles on a daily basis. They make this look easy and they make my job extremely easy. So a special thank you to the AEE staff. So we're going to be mixing up things today. We're going to have our conference sessions in the morning with a closing in the afternoon. So beginning at 9 o'clock, 9 until 11, we're going to have 2 concurrent conference sessions, the future of energy storage, and then secondly, we're going to have renewable energy plus energy efficiency plus demand flexibility equals decarbonization. The virtual expo hall, AEE membership booth, certification booth, and attendee networking will be open from 11 a.m. to 1 p.m. And we're going to wrap up and close out AEE West with a fantastic closing plenary keynote session. We've got a lineup of all-stars within the energy industry to close our event. We're going to have Dennis Hayes, the president and CEO of the Bullitt Foundation, Mona Tierney-Lloyd, head of U.S. Public Policy for Enel North America, John Puskar, Dr. Timothy Unruh, Executive Director of the National Association of Energy Services Companies, and Paula Glover, President and CEO of the American Association of Blacks in Energy. So enjoy the final day, day 3 of AEE West.
Hi everyone, welcome to session 1C. It's crazy times. I hope you appreciate my hair. But we've got a great lineup. The future of energy storage is really the future. So we've got some great speakers here today. And I'm going to start with our first speaker, who is Abdi Abdati. He currently works as the Senior VP of Technology Services at Logical Buildings. He has a decade of experience, 500 plus commercial buildings. He is involved at all levels of building auditing, wireless protocols, project management, and he regularly works with grid operators. He's got a lot to say, so I'm going to turn it over to Abby right now. Welcome, Abby.
Hi all, my name is Abhay Ambati. I work with Logical Buildings. Logical Buildings is a data-driven smart buildings services and solutions provider. And I lead the technology deployments in all our buildings as well as smart buildings. We are venturing into smart buildings arena as well, nationwide, from IoT deployment to distributed energy resources like DER. Over the last few years, on behalf of our owners and operators of our, of our clients who are the owners and operators of built environment, we started assessing the policy and technology environment for indoor behind-the-meter battery energy storage systems, and in fact commenced work on a lithium-ion battery 144 kW and 240 kilowatt-hour system indoors, just north of New York City, currently in permit stage. There have been some delays due to the pandemic, but we are back on track. From the beginning, we had a series of design and construction challenges we set out to mitigate in concert with a very highly motivated client, various state agencies, battery safety experts, design engineering consultants, architect, the site staff, and of course the utility. Based on the lessons learned, in this presentation, we lay out a design and construction model for a scalable, safe, and super efficient deployment of behind-the-meter indoor lithium-ion battery systems. Just very quick infomercial. We at Logical Buildings devise and deploy a low-cost and no-cost technology solution stack to acquire data in real time from inside the building as well as outside. We call it the SmartKit AI platform. And we don't stop there. We use the data to effectuate change. So in in a 280 character centric world of Twitter, we would call ourselves people first, mobile first, IoT first, data driven, technology agnostic, smart buildings, and cities platform. So for an effective, safe, and economical battery system deployment, we advise a top-down approach, portfolio, cohort to buildings, and not a bottom-up approach. No matter how attractive a battery system seems to be at a building you happen to visit, and I say this with experience. So at the very highest level, at the portfolio level, the first step would be bringing data transparency. Data transparency should and must be your first step in the battery system's design and construction journey. Interval meter data from especially the electrical meter you may connect your battery system to is critical information. Building can be master metered, may have separate service entrances with their own utility meter, may have shadow meters downstream of a utility meter, or maybe sub-meters. See that data, get access to that data, visualize it, and analyze them. Utility meters typically provide multiple options for data output or sharing. Make use of it and tap into it. Some options of data interface may be free. Some may come at a cost if the cost is not accounted by the utility rate case. Also understand how billing demand actually gets calculated. In our experience, battery system models from vendors were mostly incorrect. The calculations were not exact. Additionally, if you have access to building management system or building automation system or any other distributed energy resource data in the building, get access to that, overlay that, get that load level characteristic. Certain loads have higher startup power consumption, and which may eventually trip the distributed or DER assets like the battery. And this has happened in some of our buildings, especially cogen buildings. At the portfolio level, it is beneficial to have a very high level understanding of the building systems. When you're looking at a wide portfolio, get an understanding of the building systems, which will be on the same electric distribution network the battery system will eventually connect to. Are those systems in each building, are those manageable or not? We have realized with experience and through modeling, dispatching batteries when building is peaking and modulating building systems or loads in tandem can be very synergistic. 1 + 1 would be 3 in that case. What is the degree of the modulation you can achieve in those building systems? You want to know about that. For example, you may be able to raise thermostat set points by 5 degrees, or you can raise the condenser water set points by 2 degrees. You have to decide on that. So it's important to consider building systems when you're studying at the portfolio level. Review the incentive landscape, again at the portfolio level. Tons of incentives are available at the state, federal, utility, local. It helps in building a cohort of building locations later on to have this information early on. In the battery systems world, continuous change in the incentive landscape is just one constant you can be assured of. Stick to the incentives you have originally modeled, assuming the money is locked in, and the one which is agreed by all project stakeholders. Jumping the incentive ship, if you may, can prove to be tedious, but more so time-consuming. For fairly established technologies, and battery happens to be one of them, incentives only go down with time. They don't get more attractive over time. So fairly established technologies, the incentives keep going down, so you might as well latch onto the one you have right now and one which makes most financial sense. So once we are done with the portfolio level analysis, we move to a cohort level where we are looking at a group of buildings which can be good candidates for a battery system, and as a group or sometimes independently. So when I meant a group, they can act as a virtual power plant. First thing we develop is at the cohort level is a value model, and the value model would have a number of value streams listed, are a couple. GEB, or grid interactive buildings, or demand management is one, where you're determining what is a realistic demand reduction you can achieve, which can help address your billing event days. What are the DR, or demand response programs, out there your building can actually enroll with? That is another value stream. And try to understand if there is any monetary penalties for non-performance. A voluntary program is better, initially speaking. And again, if there is any on-peak, off-peak rate spread accretive enough at different battery system sizings, while accounting for cycling losses, that is additional value stream. And you have lead enablement, where certain lead credits are available, and to have behind the meter storage or some kind of dispatch model along with solar. And remember, it's always better to have these systems, if it is financially viable, at the construction stage and included in the construction budget, as opposed to getting a battery into an existing building and tapping into OPEX or CAPEX budgets of the building. We found that amongst the cohort, the pros and cons of the physical location where the battery system actually is placed proves to be very crucial. It goes without saying, as-builts are better than design drawings, and physical field measurements are even better than as-builts. But there's more to assess at a physical location. For instance, what do you see in this site picture? Do you have enough clearances? Horizontal, vertical, is there space on the wall? What is the expected temperature range of that room without a battery system in there? Is there an existing exhaust system? Is there makeup air vents? Any active mechanical cooling? Where does the condenser go? Construction fire rating of the walls, the roof, so on. Fire alarm and fire suppression availability. For example, in our building projects, we evaluated multiple physical locations at the same building and weighed their relative merits and demerits to narrow down to a location for battery. This is one of the important ones. Getting to know the general interest of the AHJ, or authorities having jurisdiction, is another important metric to consider at this level. What is their general comfort level with battery systems? Remember one thing, you are running the show, not your battery provider who thinks the township is okay, and not your design consultants or your contractor. You have to ask the right questions up front. Otherwise, there may be potential budget overruns, scope creeps later on. Battery system is a fairly familiar technology in certain jurisdictions, but generally a rarity in many others. So if possible, talk to the building inspectors, propose the system size, battery chemistry, physical location, without going into the code details, address some of these aspects listed here. Like for instance, what kind of hazard mitigation analysis do they require? If there's a certain format and so on. So at the cohort level, existing building system design directly impact the choice of the battery system, the possibility of a DER integration, like a solar PV integration later on, or the shaving of high peaking electric loads in the building. So understand the riser diagrams, the building system itself. One random comment I would make from experience is if we early on choose a battery system which is rated for 277 480 volts, then it cannot work seamlessly in a building which is having 120 208 volt service. And forcing one would mean you have to add a step-up transformer, add additional cooling, which would impact the pricing and the timelines and the scope. But also try to see if there is any integration opportunity, maybe later on for DER assets, whether we can tie into a solar PV or building integrated photovoltaic later on. Try to think about those. So once the building is narrowed down for install, ensure a project structure is in place. Work closely with all stakeholders. And stakeholders is not a homogeneous mix. They all come in, they have different understandings of the technology, the value proposition. So some degree of education and guidance is required there. So work very closely. Another piece I would like to add is the purchase method. How the method of purchase is structured. A lot of times determines the dispatch control logic of the battery system. So think about those. I would advise, defining a control logic for the battery system at the time of purchase itself. All-round education is very accretive. A battery system 101, like what does it do? Components, emergency contacts, and in fact, a full emergency operations or management plan, training for first responders, egress paths, signages will really improve confidence of all site staff in this project. And the word passes fast from site to corporate and vice versa. Also, some aspects are already detailed as part of code compliance or detailed in standards like NFPA 855, 2018 IFC codes, and so on. Site logistics comes as next logical step to consider in the design development process. Clear communication with site staff about electric shutdowns, duration of that shutdown, involving stakeholders will really help the project schedule to be on track. Simple processes such as storage require extra oversight. Ensure the batteries are handled correctly, not punctured, stored in safe locations with no condensation, no combustibles close by, or as per maybe 2018 IFC. And by the way, all these things are again codified and discussed in codes and standards, but sometimes projects tend to be associated with a standard construction job, and not enough oversight is given to some special features of a battery and inverter system. Battery systems don't get installed and operate in complete isolation. There is plenty of interface with existing building systems. One should plan in advance. For example, the fire alarm, the smoke detection will absolutely get connected to the existing fire alarm control panel in an existing building, or the air conditioning in a battery room may need taps into existing condenser water line. You may require a spare breaker to tie in on the electrical side. In our project, we had a bus stop. Think through all this at the design stage. And IT can be a completely separate animal in itself. Many battery systems, especially the ESMS or the storage management system, have certain services on the cloud. Make sure to work with your IT early on, have a sufficient bandwidth, firewall should be aware of it, make sure the port exceptions are there, and also make sure the physical layer infrastructure like Wi-Fi, Ethernet, or cellular is available where required. Last item on my list, which I believe needs its due attention, is the final testing and commissioning. Ensure there's a commissioning plan and it's part of the scope. And a commissioning plan is essentially the overview of the processes, the roles and responsibilities, procedures, plans, specifications, all the activities which need to be taken, which should take place during a commissioning, should be listed there. And it should be built into the scope of either the installer, the commissioning agent, or the EPC. And for your information, like commissioning plan is again detailed in NFPA 855. So also remember, any deficiencies, open items need to get communicated to AHJ and followed through and closed. I have seen many incomplete or marginally complete projects, especially in the DER space, to make sure commissioning is done and followed through. So that was my super condensed presentation. To summarize, we see that behind the meter, indoor, electrochemical, electrical energy storage, in this case, lithium-ion battery chemistry is here to stay. As the technology keeps evolving, and if due thought is given to safety considerations, codes, and standards, a project is viable and accretive. With that said, happy to hear any questions, discussion points, anecdotes. Thank you very much.
Thank you very much, Abe. We've got a little bit of time here for questions. And Abe, I'm going to go ahead and start if that's okay with you, because you started by saying you have to go top down and not bottom up. But after you said top down, then you went into a lot of the information that people at the top don't really understand, the meter and accessing and can you talk about, I mean, in my mind, what you described was mostly the guys at the bottom working. And if you don't have, I feel like if you don't have them all on board with you, they're going to say, oh, there's somebody coming from the top down that don't know anything about our plant. So can you comment on that relative to top-down approach?
Yeah, sure. So I would actually reverse the case and say that in a bottoms-up approach, where you walk into a building, you find a great physical location, you think that this would make perfect sense for a battery system. One realizes that until we have the data coming in from the meter, and until we know about the building systems, that kind of an approach can backfire. Because once we start seeing the data, and if we are already, if we have a battery system which is already sold to us in a way, then we are kind of cornered in such a situation where we have a certain kind of battery system, we have a certain size, and then we have to make it work in that building. And then we realize, because of various reasons, because of the building mechanicals and the electrical, maybe because of the demographics in the building, if it is a multifamily building, for instance, the profile can be completely different from what you were expecting it to be. No two buildings, even with the same orientation, with the same kind of building systems, are alike in terms of their profile, in terms of how they operate. It's just the way it is. And no matter how well every commissioning process has been taken care of. But from experience, I can say that every building is different, and battery systems are generally something which the driver is mostly on the corporate level, where they want to get into DER space and get into sustainability and so on. And I believe the approach should be much more at a portfolio level, that these are my buildings, these are the footprints, energy footprints of all these buildings. This is my load factor for each building, and these are the tariff these are the, maybe that might be the better way to approach, as opposed to just going into a building location and falling in love with it.
Okay, I have a question. And can you hear me? Everything is locked on my screen for some reason. But there's a question in: how will the design construction differ if you had lead acid batteries instead of lithium ion?
Yeah, so Prior to lithium ion being a standard behind the meter battery system, lead acid was an option. And lead acid has plenty of literature available out there. It's an industry workhorse. It has been there for over 100 years. Um, and clearly it has some benefits, like it is low cost. There is a lot of literature available. From a fire safety perspective, there is again a lot of demonstrated work done. I do not have a demonstrated experience in lead acid battery per se. However, just the energy density of the lead acid battery makes it physically not viable in most of the buildings we walk into. It just requires a massive footprint. That said, uh, the way the standards are today, the way the codes have been written now, I would say that to ensure compliance requirements are met in a lead acid battery, you have to address a lot more things than you would do in a lithium ion situation, where, for instance, in lead acid, you have to address exhaust ventilation, you have to address spill control, spill neutralization, something you do not address in lithium ion, which you can kind of pass if AJ is okay with it. And besides that, even in lead acid, just like lithium ion, you have to address thermal runaway issues and provide compliance. You have to address explosion control. And again, it is at the discretion of the AHJ. But in terms of the balance of systems and all these compliance requirements, lead acid, there's a lot more which has to be done for getting the lead.
I think you answered the next question. I'm going to read it. I think you've actually answered it. Does one have to comply with all the standards pertaining that we're typically used to for battery storage? And it sounds like the answer is very simple, yes, based on what you just said. Do you want to comment on that? And have you had to go through any of the hurdles associated, like we always do with any construction project, getting approval from the authority having jurisdiction? I think I've lost you. This is a bit of a new format, so for anyone listening, there's been a little bit of a technical difficulty. Just stand by.
Testing battery characteristics for solar mini grids operation at high ambient temperature. I'm Hasna Khan from PSL USA. This project was done 2 years ago, and we have been working on solar mini grids for a long time. So what happened is Rockefeller Foundation wanted to do solar mini grids in India, and they sponsored this project to find out the workability of mini grids at high temperature, high ambient conditions of developing countries. So that's the purpose, and to check the battery performance under different loads, simulating rural mini grids. In India, what we have done is set up scaled models for 3 solar mini grids working simultaneously and configured to operate as independent rural mini grids with a daytime load and battery charging from solar panels and nighttime load supported solely by batteries. This simulation was done in a space that has been temperature controlled room with a moderate 25 degrees C and high temperature of 40 degrees C ambient, simulating what it would be the condition or operation in the real field situation. The programmable load simulator was used because that's the only way we could have the battery and the load with the PV system operate, which resembles exactly what a mini grid does. So each of the 3 beds operated simultaneously, and they were charged identically under the same conditions. We have seen that a PV module connected to the inverter and the battery set when it's up in operation, it generally goes through various degrees of changes in the system. And in order to simulate all of that, we used a facility which was a test facility in Delhi. I will show you what the operating area looked like. And if it was for, unless it was for India, we would not get the actual climate, the winter, the summer, and the rainy seasons in simulation. And the study had actually gone through a series of tests, which is to test the battery characteristics. After that, we came to solar PV simulator. And this is the picture of the PV plant and outside the Tata Power DDL area, which is in Delhi. What we shall do is explain to you as to what are the mini-grid test beds for this simulation. The first one is an UltraFlex battery by eColt. As you can see in the picture here, the test bed has eColt UltraFlex battery set of 16 monoblocks connected to the inverter and the charge controllers. This is a hybrid inverter. And UltraFlex battery stack comes with its integrated BMS. So at the very initial stage, the system was separately checked for characteristics using the standard test procedures. And once we moved from the individual test to the PV simulator, what we had to do was create some simulation loads. As you know, mini grids go through variation during the day and variation during the seasons. And all of that is coupled to what is the load on the consumer end, which was an important part of this simulation. What we had used over here is the AHI, which is the aqueous hydrogen ion battery by Equan. At that time, in 2017, this was an emerging battery, and we managed to take this to the site. And what you have here is an 28 kilowatt hour battery stack configured with 9.2 kilowatts of PV and coupled with a 60 amp and an 80 amp charge controller. The UltraFlex battery was the first thing. And then with the Aquan battery, we have the 8.8 kilowatt hour battery stack connected. This is a picture which shows the battery stack on the right hand side. And it is quite uniquely different from regular batteries that we are familiar with. And each of these stacks are of the order of 120 kg, so very heavy in terms of field mobility, but it's a stationary battery and robust for that purpose, as a stationary battery. The AHI test bed was connected to 5.52 kilowatts of power PV and 80 amp charge controller, as you see over here. One unique thing over here is the Aquan battery has an integrated stack monitoring interface. So that monitoring interface is used for measuring all of its operational characteristics with the current voltage of these individual cells in there. And this test bed is also a parallel test bed as the UltraFlex. The mini-grid test bed for lithium-ion battery is the third battery test bed that we have. The Panasonic lithium-ion battery is being used in this test. And this is 5 parallel systems, as you can see over here. The lithium, nickel, manganese, cobalt, the NMC chemistry with a nominal voltage of 46.8 controlled by its own integrated BMS. So this is the third emerging battery type that we have taken in this whole simulation process. The microprocessor-based multi-channel analyzer has been used in the test configuration. This includes a high-speed communication data collection from 3 test beds simultaneously. That was the advantage we had in performing this experiment, is giving all of the test beds the same environmental condition, the same PV insolation, and simultaneously going through the simulated load, and which was an effort of nearly 2 years. And the value of that will be shown when we go to our next analysis. So the PV system, the battery capacity, inverter size, all of them represent a scaled down model of a typical mini grid. The system has been set up just as it would have been for any typical off-grid PV power plant. The manual involvement is very limited. It is limited to programming electricity usage pattern as load profiles on the automatic load simulator. In case we have to change the load pattern, that's the only time there is any manual interference. Otherwise, running the data acquisition system in case there has to be some work on that. And the last is in case of emergency, there would be any manual intervention. Otherwise, it's a day-long process, programmed load pattern with the natural insolation. So that's the key thing about solar as to how well the load is simulated. The procedure taken up was the PV arrays that charged the batteries, and the load simulator generated various kinds of energy and power consumption patterns. As we know, the rural consumers have typically small loads at a household level, especially during the daytime, where larger loads in the evening time, larger in terms of accumulation of loads, whereas commercial and enterprises, they have daytime loads, and which can often lead to some sudden loads like a drill machine or other water pumping, etc. So the load profile based on data from active mini-grid scenarios are programmed into the load simulator. What we shall see is the system and the load simulator is programmed to start from 10 a.m. to 10 p.m., whereas a PV starts 7 in the morning, perhaps. And the data simulation system simultaneously records the information on the load, the current, the voltage. And again, as we shall see, the load profile at 40 degrees C would not really know what the temperature is around in the surroundings, but the battery and the inverter, which is inside the simulation room, typically experiences the high temperature. If you think about it, an up profile for daytime is starting at 10 a.m. as you see in this picture. So what will happen is, if we go back from the load at 10 a.m. all the way to the evening, the 40 degrees C consists of combination of several. Where did the profile come from? It comes from a combination of several paths. For example, you have here at very early 9:50 or 10 o'clock, a low load, which is going up through a combination of several resistive and inductive loads from the load bank. And then the motor loads come that we added were about 0.6 kilowatt drill and a 0.6 kilowatt blower, added on 1.8 kilowatt of submersible pump in combination. And that's how this profile was generated. In order to give a stress test to the batteries, we have introduced 3 kilowatt load applied on top of the base load for extreme stress conditions. And because this 3 kilowatt load was not available simultaneously to the 3 test beds, it had to come in sequence, but very close to each other. And therefore, immediate response of the 3 battery types was evident, and sizing of the mini grid was important. sizing of the battery and the mini grid itself was important, we used the recommended DOD, depth of discharge, from the battery manufacturer. Because if you think about it, we have to achieve homogeneity in the usable capacity of the batteries. These are 3 different manufacturers coming back with the commercially available sizes. So we had to go around and curtail such that using the 4 stacks of the AHI battery, happened to be 8.8 kilowatt hour. We used 2 strings of ALA and 3 modules of the lithium-ion battery. This represented usable capacity of 8.8 kilowatt hour for the AHI, assuming 100% DOD. And again, similarly, the ALA and the lithium-ion battery. So now the question is, how much does the ALA allow us to utilize? They do not recommend the battery be discharged below 30% or be charged above 90%. So it's a 30 to 90 degrees range that is the suggested range for the ALA battery. So we have a 60% usable capacity. And whereas for the lithium-ion battery, the manufacturer would allow a DOD of 93%, and that was taken into account for sizing. Whereas for the AHI battery, we had a liberty of using 100% of the DOD. So what happens in the battery's life is the very critical thing, the state of charge, which depends upon how much the depth of discharge has gone through and the cyclic life, because through each cycle it may reduce some of its original capacity. So we had to go through all these test situations in order to simulate the test bed. Having said that, if you see on the right-hand side the results as to what we have observed, the AHI battery has responded very well with the stress load coming from the 3 kilowatt load. Same with the ALA battery and same with the lithium-ion battery. So all of them, the yellow is the PV solar charging, then the load, and then the battery in the blue, load is in the red. All 3 batteries have performed through the whole day, went all the way up to 10 p.m. and have successfully gone through this test. What happens is, in real case scenario, where you do not have much control on observation versus management of load locally, which is happening, one has to rely on the battery's state of performance. So it is the manufacturer's description of how the batteries should be used and keeping it within the limits of depth of discharge. We have made a certain type of findings in our test, and I would say we monitored the current and voltage as indicators of the battery performance and its health. Apart from being able to provide enough energy, as I've shown you before in the last slide, it also had to do with how well did the battery perform internally, which is not measurable from outside. So here are the results from the current and voltage. As you can see, the AHI battery has been consistent to its control tests that we had done separately, whereas the other batteries also did the same performance. The AHI has a dip in the voltage, which is a voltage drop after introduction of high power loads. So this, not being a power battery, this is more of an energy battery and a stationary battery, it experiences that voltage dip and with a high introduction of high power. So as you see here, around that time, after 11 o'clock, there is a dip in the voltage and the current, and although it recovers, that dip can be an important step. If the load was even higher, then the dip would go even lower, and the battery may cause the mini grid to go into standstill. So that was a limitation we observed with the AHI, although it has a very broad range of power and voltage that it works with. So, and whereas the lithium and ALA battery performed perfectly fine in terms of the voltage variation. The lithium-ion battery, as you can see in the last graph at the bottom line, that has a very uniform voltage. So it can take up the variation of the power demand in a very smooth fashion. What we found in the overall system is if you have battery technically viable, they also need to be commercially viable, which means when a cost of the battery is high, the capex, then its availability to the project team becomes more of a burden, financial burden, than a technical operating lifetime issue. So what we shall summarize in conclusion is a little bit to the effect that the lithium-ion battery has a combined benefit of both the batteries that we have tested. How did we come to that conclusion? So amongst all three, the advanced lead acid battery, which is an ALA type that we call ALA battery, has a ultra capacitor in the plates, and therefore it's a modification of the regular lead acid battery. It sustained high power discharge for a long time during the stress test, simulating a sudden power surge with motor. So that motorized sudden load, it could take very comfortably, very easily, because it's a power battery. Another strength of the ALA battery is its high charging capability and discharging capability, which may not be as important in terms of a mini grid situation, because our charging is from PV, which is a low C rate charging. And therefore, this is not very uniquely important unless there is a diesel genset related charging, which would require a high rate of charging. The battery is demonstrated relatively flat operating voltage as a function of SOC. This is another important thing as to how the battery voltage changes with the state of charge. As long as it's flat, its operational characteristics would be more accommodating towards the loads on the system. It's less sensitive to temperature rise. And limitation, I would say, is it's designed for partial SOC operation and strictly remain within 30 to 90% range. This may not always be possible for a solar mini-grid situation. On a monsoon time or overcast time, the battery may experience lower than this in state of charge, and that is not recommended by the manufacturer. For the aqueous hybrid ion, this demonstrated the highest operating voltage along with a wide operating voltage range. This, when compared with what we tested, what happens is you have the highest energy transfer per amp hour discharge. So with the same amp hour discharge from a battery of other kind, the AHI battery would give the largest energy into the system, which is a major advantage. Another major advantage would be the battery can lead up to 100% DOD repeatedly without any degradation of the original capacity, which was observed even at higher than recommended discharge rates. I think this uniquely defined the battery, the Equan battery, that the DOD 100% utilization of its capacity is very unique. It's suitable for long duration, relatively slow charge discharge, as I mentioned earlier, especially for residential and commercial small loads. So it's a stationary battery with its own advantages, but its limitation is it cannot sustain high discharge rate for long period. Therefore, this battery will not be ideal for cases with high power discharge, like very large commercial loads. And one has to understand what kind of situation we put this solar mini grid. So finally, the lithium-ion battery that we have used is, in principle, there are other batteries with the similar characteristics, other lithium-ion batteries, but we find it's expected to be, it can apply for other brands as well. The one we have used is from Panasonic, but that's a NMC type. the battery appears to be stable under high temperatures, and its discharge capability, voltage versus SOC, remains relatively constant. So for the various discharging rates, we could utilize its capacity, and it could endure the conditions as low as well as high operating loads. The battery has usable capacity of 80 to 90% and hence very suitable for mini grids. The battery has performed well in high power tests, and I think altogether our conclusion was that the lithium-ion battery has a combined benefit of the advanced LA and the AHI battery, and it's best suitable for mini grids. Now, in the recent years, we have definitely seen the lithium-ion batteries go down in price, and we are expecting this to be the mainstream battery for the upcoming mini grids, while newer emerging chemistries are in the process too. So that is all about my presentation. Thank you very much.
Terrific, Hashna. Thank you so much. We've got a number of questions, so I'm going to go right to them. First one is, please, could you tell you what tool you use to do your simulation?
These are the, yeah, go ahead. Finish your question, please.
What was the actual platform, the tool itself?
Yeah, for the load, we had to go through a series of trials as to what would be the best way to come about. And as I mentioned, in reality, the distribution of load throughout the day changes in a mini grid. And we're talking about developing countries, so it's not like an uniform load that you can expect. You're left with what people would be using under a real situation. And household loads in daytime is much smaller and lower in the rural areas, whereas in the evening is where the peak comes up gradually from 6 till 10, and then it tapers down again. This is the household type of load. When you go into the commercial loads, which are like small markets and such, we have observed that daytime there are small commercial applications which, although small, when they add up, it can become significant. And this is typically small shops using drill machines, using refrigerators, or other appliances that use like a copy machine, things like that. So all in all, it's a kind of a random distribution of when they come up, and putting it up in a simulator was not easy. So what we did is we followed profiles of a solar mini grid that's in operation in Bangladesh, which is in an island, and we followed their load pattern for a few cycles, quite a few cycles. And similarly, we did another one from Tara in Bihar, and came back with an order as to what it should look like. And this was done through 3 parallel load banks with individually controlled. And we have some system of resistors and capacitors and inductors. All you can program together to set up the profile that we had wanted to simulate. And on top of that, there were these motorized loads, which were separately done. And this was quite a synchronization issue that we had. And a combination of these loads to resemble the original profile was done through our system that we set up in Delhi.
Okay, and so it sounds like there was no simulation tool per se, that it was actually a custom. You had to really do a lot of custom work to do this, to pull this off. Is that right?
Yes,
right.
It was.
Okay, so next question, the next question, which is actually pretty good, and I'm going to read it, but then I'm going to paraphrase a little bit. It says, what was the overall motivation behind the battery test that were performed under this project? And as I read that, I think it's more like, who funded this and why did they fund it? So what was the overall motivation behind the project?
Okay, well, unelectrified off-grid areas in the developing countries, they are the ones who needed this solar mini grid as a solution. And we've been working on this since 2010, how to get electrification in those locations. And it is Rockefeller Foundation who wanted to put up a large number of mini grids in India. And for that work of theirs, they took ITT, Institute for Transformative Technologies, coming out of Berkeley, Lawrence Berkeley Lab. And I was helping them with my experience in the mini grids. And so the intent was to bring electricity to the rural off-grid areas of India, which means it's not as predictable as you have in a urban scenario or a certain industry where your load is under your control. And moreover, the motivation for the battery testing is even more important because many places within India are experiencing in summertime very high temperatures. So all in all, a battery experiences the worst technical problems in the operation of a mini grid. During summertime, it can have partial charging due to monsoon and overcast. So therefore, they have the same load in the evenings, whereas the during daytime charging was minimum. So depth of discharge for the batteries can be extremely critical to the performance of the system, especially if the temperature goes up, then it's even harder for the batteries to adjust to its original life. So the capacity as a function of temperature is a very critical item that we wanted to investigate. Then the input-output characteristics as to how well it actually sustains, and the impedance change. So all these different characteristics of the battery needed to be looked into, and Rockefeller Foundation was interested in supporting India's mini grid program, which they are still supporting with Tata Power. And we had the opportunity to work on the detailed configuration of what the systems should look like.
Okay, and then the question that came up next is about scalability. Once you get these systems in, how easy are they to scale up? In other words, here's the question. Once installed, how easy is it to expand upon for future growth?
Yeah, scalability is the whole mission, because you don't want to do one system for itself, but you actually want to scale it up to go ahead and apply to similar circumstances. Country to country varies. We work for mini grids design for Nigeria, and there the simulation that we see over here is appropriate as far as the batteries are concerned. As far as the load is concerned, it could be different, but it is definitely scalable because the system is uniquely tied together. The PV, the inverter, and the battery, they are tied together, and as long as it performs through the whole variation, it is scalable.
We have time for one more. What are the critical parameters that are unique to batteries used in the solar mini grids in a developing country? So what are really the unique parameters? Okay, we've lost Hasna, it appears. I'm going to go ahead and introduce the next speaker. Should I wait for another minute or go ahead and introduce the speaker right now? Oh, okay. Hey, I'm real excited about this next speaker. It's Dr. William Conlon, but I call him Bill. I call him Bill. I don't know him that well, but he's been around for years. I've been aware of his work, and he is he's the founder and president of Pinto Power. But more importantly, he has such a good perspective, like a hands-on, career-wide perspective on power generation from nuclear and fossil fuel-based to solar and combined heat and power construction and commissioning. He's a really well-versed guy, and I'm dying to hear his presentation on this technology. So, Bill, go ahead. It's all on you.
Well, good afternoon, and thanks for your interest in energy storage behind the meter. And in particular, I'd like to introduce you to hybrid energy storage. So let me tell you a little bit about Pintel Power first. Our mission is to bridge renewable and conventional energy via dispatchable, large-scale, long-duration storage of excess wind and solar energy. And we do that through hybrid storage systems that I'm going to tell you about. The challenge that we face behind the meter is that with distributed energy resources, the investment, operation, and ownership of the assets is distributed, and the interests don't always align. Load-serving entities like utilities or cogen systems serving a campus are affected by all of these things outside, but they don't control them. And the visibility of generation is restricted really to the off-taker or the producer in the case of net energy metering arrangements. So DERMS and blockchain are unproven means of managing this. So we think that long duration storage can provide a buffer to manage the variability of performance and the contracts behind those assets when they're behind and even in front of the meter. When we're talking about commercial and industrial microgrids, we know that facility energy managers need to optimize both their energy bills and their carbon footprints. And they're interested in things like combined heat and power, cogeneration, precisely to do that. Hybrids really give them an additional degree of freedom to help manage both the energy bill and the carbon footprint. And it also can allow a system that's designed and fixed in size to have additional flexibility to match variations in seasonal loads and the economic price signals from outside and inside the campus. Long duration storage can also help provide resiliency for microgrids during things like public safety power shutoffs that we've had here in California in response to fires, but also other events, whether they are weather related or man-made catastrophes of some kind. So the resiliency thing is something that comes along for the ride with storage. Now, we all know that electrical and thermal loads vary daily and seasonally. Solar production peaks, of course, during the daytime and is non-existent at night. But the loads themselves also vary. They vary with the climate. They vary around the country. They vary with the season and the daily weather patterns. The load within a building depends on its use. It may be occupancy related and varying, or it may be a data center, which is a more or less fixed load. But the important thing is we all have a commitment to sustainability, and we have to respond to the economic pressures. So flexibility improves our ability to manage and respond to all of those things. Now, when we're talking about storage, it's important to note that electricity can't be stored. It must be transformed into another form of energy for storage and then converted back to electricity. So we have many means of doing that. The electrochemical battery, lithium, lead acid, other kinds of batteries, electrochemical batteries do that, converting electricity into electrochemical energy stored in chemical bonds. Gravitational storage is probably the largest and most commonly deployed storage system in the world, and that's pumped hydro, where we pump water uphill and take it back down through a turbine to recover that energy. But that's something that you can't scale to put behind the meter. We have mechanical systems, flywheels and compressed air systems. Flywheels certainly are of a scale to be behind the meter or in a campus or microgrid application. Compressed air, not so much. It typically requires a cavern underground to make that possible. And we have chemical storage as really a future means, may be stored in hydrogen or ammonia or some other chemical system. But those are still in the early stage, and they are not really ready for deployment here behind the meter. And then lastly, there's thermal, which many facility managers are already familiar with, for example, with ice systems that might be used to assist refrigeration loads. And when we're talking thermal, we're often talking about, in high temperature, using a liquid or molten salt. You can use cryogenic air. There's some concepts out there using cryogenic air. You can use solid media like concrete. One thing all energy storage systems have in common, though, is since they're transforming energy from electricity to the storage medium and then discharging it again back as electricity, there are three components, and they all have to be considered when we evaluate them. There's a charging process, which has its own charging speed based on its power input. There's a cost per unit of power that comes in. So whether you're getting that from the grid or from locally sourced distributed resources, there's a cost associated with that. That cost may vary by time of day or season of the year. And then there's the efficiency per unit of energy that goes in. How is that electricity transformed, and what losses occur on the way to the storage medium? And when we talk about the storage medium, we start first of all with the duration. How long do we need it to run? And that determines a quantity of energy. Then we have to consider how much space that will require. That's the volume per unit of energy stored. And what does that cost us? Different storage media cost different amounts. For example, you pay for molten salt, but air or water are ubiquitous and freely available. Lithium batteries are quite expensive as a storage medium. So we need to balance all of those things. Each of these storage media also have losses of mass and energy. And often they have standby energy needs. For example, a battery might need air conditioning or heating to maintain the battery chemistry within safe limits. And safety, of course, is important to make sure that there's no fire or explosion or toxicity. And lastly, there's the cost and availability of the container. As I mentioned, pumped hydro, that has a container that requires geology, and those formations are not always available. And where they are, sometimes there isn't water to fill them. And compressed air often requires an underground storage cavern, which may not be available in your backyard. And then we have to transform that stored energy back to electricity. And so there's a discharging process that has a power output, a cost per unit of power, and then the efficiency. How much of that stored energy do we use per unit of energy output? So those are the considerations that are really across the board. Now, the cost of energy depends on both the form factor and the processes that are involved. So many of us are familiar with lithium batteries. They're a cellular form, lead acid batteries, nickel cadmium batteries. They're all available in cellular form. And so to get more energy, we add more cells. And then there are these other approaches: bulk storage, flow batteries where the electrolyte is stored in a tank, pumped hydro systems and compressed air that I've mentioned, the liquid air approach that's being developed, and then molten salt as a thermal energy storage medium. Those are bulk storage media. And the reason those are important is that the capital cost varies. So cellular systems have relatively low cost for the charging and discharging processes, but the cost of the storage medium is proportional to how much energy there is. That's the blue line. Whereas bulk systems, they tend to have relatively high capital cost for the charging and discharging processes, but the storage medium is relatively cheap. So we can see here there's a crossover as we go to larger scale. And when you then normalize that to $1 per kilowatt hour basis of the amount of energy that's stored, you can see that batteries will tend to have an asymptote that is fairly high, and that the bulk storage media will prevail in terms of capital cost when we go to larger scale. Another thing that's important is the round trip efficiency. How much output do we get per input? And these are roughly measured the same for both kinds of systems. The efficiencies are different based on whether it's a battery, which tends to have relatively high round trip efficiency, versus some of the others that are thermal or mechanical processes that have lower round trip efficiencies. So now we see that we have to balance the capital cost from the previous slide with the efficiency. Now, in the facilities business, we're all familiar with combined heat and power. And in a CHP system, what we do, we need two forms of useful energy. We need electricity from a power plant, and we need thermal energy, say steam, from a boiler. And we can use fuel into two different pieces of equipment to provide that. Or in a CHP system, we can use that fuel and get the two outputs from a single system. And that allows us to get more energy from a single input. So now that's going to set the stage for hybrid storage. In a hybrid storage, when we're talking about hybrid with, for example, combined heat and power, it's a means to further reduce cost. Here, we have two energy inputs, electricity, for example, coming into storage, and waste heat of some kind coming into storage. And in addition, we have fuel. And then we have useful heat and power. So there's multiple energy inputs in the storage system and two energy outputs. So just as you can imagine in a CHP system, determining your efficiency and the relative value of electricity and thermal energy is important. Likewise here, where we have multiple input streams and multiple output streams, the economics requires some careful analysis. But what we do get is flexibility in timing of when we put energy into storage and when we take it out, and flexibility in the split of how we use that stored energy for producing electricity and useful heat. So let me tell you about one approach to that of hybrid storage using molten salt or liquid salt in what we call a liquid salt combined cycle. And the reason to do this is to minimize both the costs and emissions of GHGs by an optimal mix of fuel, electricity, and the use of waste heat. So we can take low-cost energy when it's available. That may be renewable energy from the grid, renewable energy locally, or energy that is produced from the CHP system, but has no use on the campus and has limited value when exported back to the grid. So we can store that energy, and then we add fuel into this system to deliver both power and heat to the load. And that allows us to dynamically match thermal and electric loads while minimizing GHG emissions and at lower invested cost than batteries. This hybridization of energy storage with fuel and heat creates a number of synergies. Thermodynamically, we get the potential for higher discharge power from the equipment. We reduce cost because we have higher storage efficiency by combining the heat from an engine with the thermal store. We remove a number of design constraints having to do with corner cases, with materials and so forth through this synergistic integration. Development is eased because we're using proven components in the system, thermal components that are familiar and understood and available from a supply chain of manufacturers of engines and turbines and heat transfer equipment. The storage footprint is greatly reduced compared to alternatives because of that storage efficiency. And we add flexibility to match thermal and electric load. And finally, this approach allows us to reduce fuel consumption by optimally displacing fuel and replacing it with electricity when that's economic. So here's one example. There are many ways of implementing a hybrid system. This one shows hybrid storage with an engine plus a peaking cycle plus useful heat delivered to the load. So we're showing connected to a utility. We have a load and we might have distributed renewables attached to this campus. And we have 4 basic components. Let's start at the bottom with a thermal energy storage system. It's a 2-tank, in this case, 2-tank molten salt system. And that molten salt is heated either electrically using charge power from the bus when that charge power is economical, and is heated by waste heat exhausted from an engine. And that could be a reciprocating engine or a combustion turbine. So that engine then can be cycled on and off as needed, or it can continually run, and its waste heat can be applied either to produce useful heat for the load, or stored for later use either as useful heat or as power. And then we have a bottoming cycle, which in this case is shown at the top, which would be a Rankine cycle of some kind. In the case where we're talking about heat delivered as steam, it would be most convenient to use a steam cycle, but an organic Rankine cycle could also be used in these cases. So here's a system that would allow one to optimize both the delivery of electricity and steam to a campus, and optimize the use of power from whatever source, maybe a time of use rate that's available from the utility, or excess distributed renewables that are available, to optimally drive delivery of energy to the system. And by sizing the thermal energy store appropriately, we can greatly aid resilience and manage these thermal mismatches that are caused by varying load that the customer or facility might have. So
Bill,
I want
thanks
to
a
thank
lot.
you for your attention, and I look forward to your questions, and I'm happy to provide more details. In fact, if you would like more information, please contact me via email, or call me, or take a look at our website. So thank you very much.
Bill, thanks a lot. We have a number of questions coming in, but the nice thing about being moderator is I get to ask the first one if I want. Hey, Bill, you know, I am on in my career like you, and I have seen this huge move towards electrification. And when I look at the numbers of a combined heat and power plants, many of which I'm seeing phased out because they don't want to have any fossil fuels. If I look globally, if I look locally, they're losing huge savings in money, even though they're getting significant local savings in greenhouse gas. But then when I look at it globally, there's really kind of a net not savings in greenhouse gas. It's almost like they're sacrificing their savings and the ability to electrify, which is the current trend, at the sacrifice of long-term global decarbonization. Can you comment on that relative to both the savings associated with what you're talking about versus, let's say, the more electrification type of systems that are coming in now?
Yeah, I think that this is a big challenge for us as practicing engineers. We're committed to the sustainability efforts, and the question always is, are we truly in the think globally, act locally? When we act locally with an electrification measure, is that truly going to have a global impact on decarbonization? So often what's happening with electrification, sometimes it's done purely with the paperwork, with accounting. We buy renewable energy certificates, and that then allows us to claim that our overall annual energy use is carbon-free. But that misses the fact that the use of energy, of electricity, is not time coincident with its production from solar panels, for example. And so in that case, we see many large companies and some prominent universities here in Palo Alto who actually can be completely carbon neutral in their campus because they've exported their carbon production to someplace else for peaking loads at night. So until we have a means of tracking that carbon and assuring that this is time coincident decarbonization, it's a little bit of a game. So as engineers, I think we have to try to bring that perspective to our clients and hope that they'll do the right thing. But there's a lot of pressure for kind of paperwork, wallpapering these issues.
Terrific, thanks. We have a number of questions coming in from the attendees. Is a fuel cell a type of chemical storage?
No, a fuel cell isn't a storage medium at all. A fuel cell is an energy conversion system that takes fuel and produces electricity and has waste heat. Now, if the fuel was produced by an electrolyzer and the fuel was hydrogen, well, one could argue then that the hydrogen is stored energy. But the fuel cell, no, the fuel cell is just one part of that, and it's the right-hand side, the discharge process of a system. It's not a storage system at all.
Yeah, I'll add to that. My firm has just designed for installation and seen installed and constructed a number of fuel cells here in California, and we had to go through AQMD for all of them. They're definitely on the conventional, current, commercially available fuel cells. There's definitely a carbon aspect to them. Next question: can you comment on any ESS work on the thermal side, diurnal or seasonal? And that's from Bill Stein, who's an AEE fellow and a life member.
So I think that there's at lots of different scales. The most common thermal storage systems that we've seen, and we have them, for example, various campuses, cogen systems that I worked on earlier in my career would have ice tanks, for example, and that would then store energy to support the chilled water system. So they might be electrically driven vapor compression systems for ice storage. We have ice systems that are in commercial installations. So I think that when we're just talking about ESS thermally, that's probably the most common. You see some that are also chilled water tanks that are used for gas turbine inlet air chilling to improve the power output of a peaking plant that has to respond on a hot summer day. So those are some examples, but in terms of hybrids, we don't, that's really what my company is pursuing. We're trying to get this idea of hybrid integration of storage out there.
Bill, how does the efficiency, let me call it a global efficiency. The question says, how does the efficiency of a thermal hybrid compare to batteries?
So this is a really a tricky one, because people who work in combined heat and power know we have systems that have one input fuel and two outputs. How do we measure efficiency? Because their values are not the same, and their measurement is not the same, kilowatts versus BTUs. So the same is true in this. So when we look at single input, single output systems, the efficiency metric, kilowatt hours out over kilowatt hours in, that's very straightforward. When we look at hybrid systems, it's tricky. And one reason is that hybrid systems often will have more kilowatt hours of electricity out of them than was put into storage. So if I told you the electrical round trip efficiency was 140%, you'd look at me like I was crazy. So we really need to separate those metrics. And what we prefer, and I'm on the ASME Performance Test Code Committee for Energy Storage Systems, and because some of these systems are complicated, we prefer to express the output efficiencies or the output efficiency of electricity as a rate. So while we are familiar with the term of heat rate for fuel, we also then have a term called E rate, electric rate. So we've got two inputs. We put fuel into it, and we put so many BTUs per kilowatt hour into the system. And then we have an E rate. We put so many kilowatt hours or kilojoules per kilowatt hour of electricity. At the end of the day, of course, what matters is not efficiency as much as maybe we have either a puritanical desire to save energy, or it's our technical background that wants the highest possible efficiency. It's the economic factors that matter. And so all of this has to be in service of these two things, the economic factors that drive sustainability issues. But to answer the direct question, yeah, batteries can often be about 90% efficient, and any thermal system based on Carnot limits, we know is going to be in the 40, 50% range. So, but if charged with electricity that would otherwise be wasted, remember that you may not know this, in California, we have already curtailed more than 1,000 gigawatt hours of renewable power this year. Okay, that's solar power that was wasted. We put in the investment and that had no home, no place to go. So that's another waste. Okay, so if we don't store that and use it later, that's also a waste factor.
I think we have time for one more, maybe two. As we reduce carbon emissions, how does this affect the worldwide carbon cycle?
So what we see is that there's two factors to it. The first is that a hybrid approach can typically reduce the fuel consumption of a plant by about 50%. So so on the one hand, you can look at that as a halfway measure. On the other hand, you can look at it as taking half the carbon out of our emissions, and that's a pretty big bite that you can do with one system. The next thing that is important is when you look at replacing our fossil fuels with hydrogen, hydrogen kinds of fuels, whether renewable or electrolyzed hydrogen, those fuels are expensive. Gas right now, say, is $2 a million BTU, but electrolytic hydrogen or steam methane reformed hydrogen with carbon capture is over $13 a million BTU. So if you can cut the fuel use in half, you can now make it economical to consider consuming and burning that hydrogen. And so I think that's the important thing in hybrid systems, whether it's a thermal hybrid like I work on, or compressed air hybrids such as LADWP is going to put into the Intermountain Power Plant in Utah that would have hydrogen storage and air storage. It's the hybridization that allows the hydrogen to be economical, and without that, it just would be too expensive. Thank you.
There are a number of questions, but we're going to have to end here. I think it's time to move on. Bill, I know that Bill and all of our speakers, I encourage anyone listening can reach out to them through the AEE, and I'm sure you have the contacts. If not, just reach out to AEE. This is fascinating information. And speaking of fascinating information, we had a technical difficulty with our second speaker, Hashna Khan, and I just wanted to make sure that she went through the Q&A, and that was not a technical difficulty, but she is the president of PSL USA. It's based in California, but she has done significant work on the solar mini grids all over the world, as a matter of fact, and that was her credentials for the really interesting talk she gave. So Hashna, I'm going to let you have a couple of words if you'd like, just to kind of re-close out your last session.
Oh, thank you so much. I just wanted to thank AE for taking me up for this presentation, and would like to encourage everybody to keep your eyes open for the energy, climate change, and storage issues that's coming up in the developing countries. There's a big potential for utilizing renewables, and I work for the development partners, and I would like to invite all of you to keep your eyes open and come forward with the solutions that I learned from US and especially California. I take them over to the developing countries, and that's a good part of my life.
Thank you so
Thank you.
much. Hey, our last speaker, it's a perfect ending of this session. You know, the future of energy storage, it's about money. And we've got the Chief Financial Officer for Energy Advisors LLC, and they have been working on a non-investment capital approach. So I'm going to guess it's on the performance side of things. So particularly as you look at all these technologies and the evolving technologies in storage, money's a huge, huge aspect, getting it going and then retaining it. So Anthony Amendola, Chief Financial Officer of Energy Advisors, I'm going to turn it over to you. I'm looking forward to your talk here. Thank you.
Aloha and good morning, everybody. Thank you for taking the time to listen to my presentation. Today, we'll be talking about efficiency and renewables as a service. And, what is efficiency and renewables as a service? And why am I speaking to you about this in the future of battery storage section? Battery storage typically goes hand in hand with solar PV, which in our world now goes hand in hand with typical energy conservation measures inside the building. So what is efficiency as a service? The two analogies I like to give first is software as a service. You go out and you subscribe to Microsoft 360 and it gets downloaded to your laptop and off you go. You can go get a disk. You don't really own the software, but you get all the beneficial use. Somebody else maintains it, upgrades it, etc. The second analogy is the solar power purchase agreement. And that really is contractually the evolution into the efficiency services agreement, whereby you get solar panels, you get the kilowatt hour output, but you don't own them. You don't maintain them. You don't repair them. Somebody else does that while you get the beneficial output. And that's really what efficiency and renewables as a service is. It's us taking that structure and bringing it inside the building and then enabling us to combine renewables with typical energy conservation measures, which in the past was not the case. They were contractually separate for various financial reasons. So, what can you include in EAAS, or efficiency as a service? So that's the great thing, is that you can include a wide array of items: LED lighting, power conditioning. We do a lot of that in Hawaii because of the power spike issue. EV charging stations, of course, solar PV and battery storage, boiler, chiller replacement, building control systems. We're also doing a lot of work in the refrigeration area. As the world is evolving, refrigeration for Amazon, for grocery delivery, that's all becoming a very important part of our world today. So whatever makes sense inside and outside your building to gain energy efficiency can be included in efficiency as a service. So what is this renewables as a service model, and how are we combining it? So historically, you couldn't include typical energy conservation measures in a solar power purchase agreement. And so what we've been able to do is, by looking at the equipment as a service item, an item that can be installed, that you can use, and then we, the developer, service it for you. What's interesting is that we no longer, for the solar PV and battery storage, we no longer require a 20-year PPA, which is mostly unheard of in a lot of areas because the tax equity structure of the PPA requires a 20-year amortization time frame. Not the same here. We're doing solar and battery storage efficiency agreements in 10 years now, which helps for certain parts of the world, Hawaii, where I do a lot of my work, is a lot of leasehold properties, meaning there might be less than 20 years left on that lease, and therefore you couldn't do a 20-year agreement because it's not coterminous with the end of the lease, which most require. So we're able to do it in shorter periods. The effective PPA rate's a lot lower because we don't need the tax equity piece, which is, as many understand, the most expensive part of it. So it gives you a lot of flexibility, So what are some of those key benefits that come out of this? Well, the first one is no upfront costs, zero upfront costs. People tend to like that idea. And so what we do is we fund it upfront. We implement all the measures. And then we use the service agreement to both amortize the cost of the project as well as service that equipment that's been installed. So no upfront cost. For you commercial real estate folks, immediate increase to your net operating income, cash flow boost, because you're getting the benefit of the savings without paying for the project. And in most cases, the savings are fairly above what you would pay for that service agreement. So you're getting an excess boost there. Eliminates the operational risk. I'll show you an example in a few minutes of a project where we could have done it in 10 years, but it was solar PV and the customer owner did not want to touch them, so we extended it to 20 years. So for 20 years, they get the benefit and don't have to really do anything to it. Asset valuation, again, for you commercial real estate folks. Historically, people have said, well, I can't do the improvements because I'm going to sell the building in 3 and I don't get the energy savings of a full 10-year deal, for instance. Well, really what we're finding is that, and this is talking with the Appraisal Institute, is that the method now is to take the annual energy savings divided by your cap rate, and that is the asset value increase of your building. And it's not complicated. If you can increase NOI, first you reduce OPEX, you increase NOI, that feeds into a higher value building. Full turnkey service, right? So depending on the customer, it doesn't have to be full turnkey, but most people that we work with don't want to deal with the equipment. And so this helps you get there. No impact to the balance sheet or property liens. Important for the financial guys, again, in the commercial real estate world, that have senior debt on the building. Because it's a service agreement, there's no lien on the asset. It's a simple UCC1 equipment filing. So that can be very important to some. It can mean nothing to others. But the fact that I came out of the commercial real estate development world, I'm pretty attuned to all this stuff, and that's why we've tried to create the model that we have now to help these projects get across the finish line. Because the worst thing that can happen is you can spend all that time and then you get down to the debt and can't get it done. So this next slide is our Kama'aina fund, right? So for mainlanders, that means local fund. We've strived in Hawaii and also in the mainland to use all local funding, right? It kind of feeds into local funding, local jobs, local profit. The money stays where it was made. That's important to us. Again, some people find that attractive, others don't really care. But we really try and localize our activity within the region that we're in. We find that to be helpful. Okay, so here's an example of efficiency as a service in action. This was by the way, this is our first project in Hawaii several years ago. It was the Malama Keola Healthcare Center on Maui. And this is an example of how short the service agreement can be and still accomplish what we wanted to accomplish from a conservation measure, is that this was an LED lighting and power conditioning project, not a large project. The CFO wanted to minimize the amortization period, so we were able to squeeze it into 3 years. And basically, the entire project is amortized, and during that 3-year period, we also service any type of repair or maintenance needed for the LED and the power conditioning. Cash flow positive day one, big positive net present value, total net savings over that period, over the life of the equipment, almost $1 million. We try and check the green box and let the customer know what's going on with carbon reduction. And so typically you can't squeeze these down to 3, but again, high cost of power markets like Maui that starts at 30 cents and goes up offers you an ability to amortize this stuff a lot quicker. So that's an example of how we can shorten it. We may go back into these folks at the end of the service agreement. Now with the COVID world, we are able to include COVID upgrades into our efficiency service agreement, and we could just extend this and then amortize the COVID upgrades over a longer period using the energy savings from the LED and the power conditioning. Otherwise, at the end of 3 years, in about 6 months, the service agreement will be done and we'll move on. But there is a lot of flexibility there in time and what we can do during the service agreement, for instance, add COVID upgrades. So it's an interesting discussion. This is the other end of the spectrum for a project. I tried to go on both ends of the spectrum. This is an assisted living project on Oahu that is LED and solar PV. So there's a huge roof area and an ability to put quite a few PV panels up in a great spot on Oahu. And they also had old fluorescent lamps all through the facility, so it made sense to do both. And in this example, it's a 20-year deal, and we could have done it in 10. As I mentioned earlier in the presentation, we have the ability to do that. But the customer did not want to touch those PV panels during that period. They want nothing to do with them, and so we've got a 20-year deal on this one. And you can see the amount of savings, 190,000 kilowatt hours being produced annually on the solar side, and then saving 88,000 kilowatt hours on the LED side. And for us, a produced kilowatt hour equals a saved kilowatt hour. It's all the same. What it means is that's just one less kilowatt hour the customer has to buy from the utility. And so from their perspective, it's dollars in their pocket because they don't have to pay for that. So this is really the pure, and this is the classic way to approach efficiency and renewables as a service, because we are able to combine them. And we're able to utilize all the investment tax credit and depreciation that you get from solar and battery storage. This one didn't have battery storage, but anyways, so we're able to do one efficiency service agreement to the customer and one contract, and then we handle the rest behind the scenes. And so when you're able to combine renewables and typical and standard energy conservation, it becomes pretty powerful, because again, if you think about kilowatt hours as produced or saved are the same, that creates a pretty compelling case for them. And right now, we're looking at projects that have chillers, boilers, building controls, solar PV, battery storage, LED, and we're combining that all together for the customer, which again, heretofore was very difficult because of the tax equity structure of a power purchase agreement and with solar and battery storage. So it's a pretty interesting way to combine these things. So with that, I wanted to keep this presentation short so that there's enough time for questions, concerns, anything that I can answer for you. Glad to do so, and thank you so much for taking the time to listen today. Mahalo.
Thanks a lot, Anthony. I've got a number of questions in my heart, but we're getting so many coming in. Let me go ahead and start with the first one that just came in from a attendee. What is the difference between EAAS and ESPC?
Wonderful. That's usually the first question I get, before I answer the question, thank you to the AE. You guys have been wonderful under a different environment now. You're having to put on this conference, but so yeah, that's usually the first question I get is the difference between ESPC and EAS, because I came out of the ESPC world, spent a few years at Johnson Controls and Canada on public-private partnerships. The basic difference is that usually the ESPC is used primarily for municipal governments where there are a lot of restrictions on the kind of things that they can do, and everything has to be guaranteed. Under our approach, the service agreement is a little different in that we can offer guarantees if the customer wants them, but I will tell you that in my experience, a guaranteed outcome on the production side or the savings side creates a bit of a difficult situation at times for the owner and the provider of that service. We deal with a lot of private ownership that want to be able to do what they want with their asset at different times, which may fall outside of some of the restrictions and goals of the guaranteed savings piece. So for that matter, we don't typically offer the guarantee unless the customer really, really wants that, at which point we can do, because frankly, if whatever someone tells you, the guarantee costs money. There's no free lunch. And so it's a little different there. The way that the debt structure is set up is different because typically, again, ESPC is a tax exempt lease or something similar that's tied to more of the municipality approach.
Okay, next is along the same lines. Can you include COVID upgrades in the EAAS?
Yes, of course you can, and that's really been a big change for us. We're already looking at projects that would be a combo, because typically if you're going to go in and do COVID upgrades, and when I say COVID, it's not just disinfection, it's now social distancing, right? A lot of these layouts in the buildings are no longer are not socially distant. So you've got to, if you think about the commercial office interiors folks and those folks, they're going to look at a major change in the way that you lay out a building. Well, if you're going to change the layout of the building, you are going to change airflows. You're going to change lighting levels. All these things that you could upgrade will save energy, and so thereby, let's look at the stuff that produces cash, so that we can pay for the stuff that's needed, like COVID upgrades. So yeah, it's a very logical connection to make at this point.
I think you've already asked this, but the next question is, how can you combine renewable and non-renewables in one agreement?
Yeah, so the big difference is the tax equity piece. That always, most of the time, created a situation where you could not do standard energy efficiency within that same agreement or within that same financial structure, because it would mess up what the tax equity does on the pure renewable side. The fact that we're not using that, the fact that we're using a different structure allows us to merge those two together, which again is logical because a produced kilowatt hour is the same as a saved kilowatt hour. And I can't tell you how many stories we've heard, especially in Hawaii, where you maximize the output on top of a building before you go inside that building and make it more efficient, which is kind of ass backwards, right? You want to reduce before you produce, so logically you go in and make the building the most efficient, so then you know what what your footprint is. And it's the same problem in the battery storage world, right? You go into a building that has been made efficient, you think you're going to need all this battery storage, and then 3 years down the road, the customer redoes the inside of the building and all of your metrics are all screwed up. So that seems to be a logical, reduce before you produce, basically.
So next question is, how is the energy efficiency part of this different from energy savings performance contracting? I think a little bit more in depth about the difference of EASS.
Yeah.
And
Yeah, so thank you. So the other part of this is that with a typical ESPC contract, you're doing only what saves energy. Depending on how the financial structure is, if, for instance, you're doing PACE funding in California, you can't include anything in that upgrade. For instance, if you're going to have to start fogging a building or whatever you're going to do on the COVID side, that can't be part of that deal. For us, it doesn't matter. And the perfect example is a solar PV project. If you need a new roof to make the solar PV make sense, that typically screws up the deal. You can't do that under an ESPC project per se. But we can include anything inside of that efficiency service agreement, including non-energy efficiency upgrades, which typically there's a lot of deferred CapEx that needs to get done that doesn't save energy and therefore won't be included. Under our approach, we can include all of that, whatever it needs to be.
this is the perfect follow-up question, Anthony. That sounds too good to be true. What's the catch?
Yeah. So the catch is, right? We're funding all these projects. They're saving a bunch of money. You don't pay anything. Wow, it's too good to be true. The customer needs to be a good credit customer. That's important. We can't, we're not doing flyer deals where the customer is questionable. So that is the catch, is that the customer has to have decent credit and is underwritable.
So,
But besides that, everything else is wonderful.
You're saying that from your side. How about from the customer side? Okay, I've got great credit. Boy, that sounds too good to be true.
Yeah.
What's the catch for me?
Yeah, well, the catch for you is that you have to operate the building according to what we all agreed to up front. And a lot of times, again, this goes to my earlier discussion about reduce before you produce, but if you're going to do a major layout change to your building, let's do that before we employ the energy efficiency improvements, because a change to the use, to the occupancy, to the length of time, that all is going to change what your savings are. And then if you increase your plug load by 25%, whatever, add a server room, then you're not going to realize the savings that were promised, because you're getting the savings, but you're adding the use on the other side. So that that is one issue that we do run into.
Okay.
But besides that, everything else is good.
There's no catch. Hey, I've got another question or two, but I just want to mention that I've been in a number of these, what I'm going to call large-scale conference type settings, and there are always technical difficulties, but this is the best one I've been in. I don't know who's behind the AEE platform and all that, but this is really quite something. And I actually wrote our CEO and told him, boy, this platform is really cool. Along those lines, I want to remind everyone who's listening here that the expo hall is open, and I haven't looked into it yet, but I'm actually going to go to it because it's like, wow, this is working pretty well. So I'm going to take a look through the expo hall virtually here, and I would encourage all of you after this is over to go into the expo hall and take a look at all the great exhibitors AEE has. Also, all of these presentations are available to you. You'll be getting them. I don't know the details, but I'm sure the people on AEE who are on this platform with me right now are going to be getting that information to you. I also want to thank all our speakers, Aspi, sorry, I go have my glasses on. Oh, Hashna, Bill, and Anthony. Thank you so much. It's really fascinating. I love this tapestry today. So other than that, one last question from me, Anthony, if you don't mind. Have you done
Sure.
one of your projects, no capital projects with battery storage yet? And tell me a war story.
Well, yeah. So that's going to be a short answer. We're just now starting battery storage projects, on the islands. It's something that uh, is now starting to come together, right? The economics are right, and the savings are right. And because I'll be honest, a couple times in the last couple of years, when I'm working with strictly commercial deals, it's a little harder because the economics was not there. But now, and really in the past couple of years, that has changed tremendously. And I'm a finance guy, so I look at everything through a cash lens, through a financial lens. And there has been a big change now. And I think just, a lot of the right things have happened, from costs going down, et cetera. And so I think, we're actually looking at 3 right now, rather large battery storage projects that will be for some larger resorts on Oahu. And so I think that is coming in a big, big way. So, yeah. So no war stories yet, my friend.
Well, listen, I'm going to end just a tiny bit early because I want to encourage everyone to maybe take an extra second to get in the hall, but get in the expo hall. It's going to be pretty good. And thank you to all of our speakers. Thank you, AEE.
Thank you.
And I'll see you at AEE World, I guess, in the fall, one way or another.
Yes.
Thanks all.
Thank you.
Goodbye.
Bye.